Alright, welcome back. So today we're going to look at relative velocity in 2 dimensions. This is covering Module 1, Inquiry Question 2. And dot point number 4, which says describe and analyze using vector analysis the relative positions and motions of one object relative to another on a plane. Now, just remember when we talk about something on a plane, we mean it's going up, down, left, right, north, south, east, west kind of orientation thing. Okay, so before we do that, let's just have a look and recap on what we talked about with one dimension or one-dimensional relative velocity. You have two cars approaching each other like so, and if we draw out the vector arrows, we can almost draw it out like this. So when two cars are approaching each other, you can almost set it out as if they were starting at position 0. So this bit here, we can call that position 0. And afterwards, they move away from each other like so. So that's kind of a similar interpretation of what we see in the diagram below. Now, when it comes to relative velocity, it is a vector subtraction. So if it's relative, you are using vector subtraction. If you were given questions where you were asked to look at net velocity, then you are looking at vector addition. Okay, so there is a difference. This one we're not covering when we're talking about relative velocity. When it comes to understanding what the question says, so usually the question will start off with find the relative velocity of object 1 relative to object 2. So the thing you're trying to find is the velocity of object 1 based on the perspective of object 2. So object 1 is going to be the positive vector in this vector subtraction, and the object relative to, or from the perspective of, so relative is also from the perspective, that will be your negative vector. Okay, so if we have a look, we have v1 minus v2. So if we're looking at this, car 2 has gone in this position here now. Car 1 has gone to this position here. Now, based off what this equation tells me is, what we'll know is that car 2 has got to be written in it or drawn in its negative v component. So at this point, we have positive v2, so the positive velocity of car 2, and here we have the positive velocity of car 1. Let's just assume the original position the cars are moving is their positive position or their positive motion. So what happens here? Car 2 going back this way, that will be v2 minus, and it connects to the car 1's line, which is v1. So the resultant line goes across like this. Just use a different color to show. So it goes along like that. That's your resultant, or this is your v1 according to 2. And that's how you do it. You could also interpret it as you have this center point here, and because this is in kilometers per hour, you can imagine starting at position 0, after 1 hour, car 2 is 90 kilometers this way, car 1 is 100 kilometers this way. So based on the perspective of car 2, this is where car 2 is now. It's looking back at where car 1 is. so from there to there, you'll get 190 kilometers. So 190 kilometers after 1 hour based on the perspective from car 2 to car 1. And in this particular direction, we can say car 1 has gone relatively speaking to car 2, 190 kilometers east. That was how we do the one-dimensional stuff. Okay, something slightly different. What if we're dealing with a two-dimensional problem? Okay, so having a look, our truck is moving 70 kilometers up this way. Our car is moving 80 kilometers this way here. Okay, so how do we work out the relative velocities of this particular scenario? Okay, now let's have a look at what we have. At this current point in time, we have a truck that is moving up and a car moving to this point over here. Basically the same thing as this diagram. What we're trying to find is the relative velocity of the car relative to our truck. So we're trying to find VC to capital T. Okay, so let's draw it out. So we know that VC to T, if we write that as a vector equation, it's positive, VC is positive, negative VT. So according to that formula, because this is positive velocity of the truck and this is the positive velocity of the car, if I want to match everything together, this line here coming down this way will be negative VT. Okay, so you can see how these two arrows now line up with each other, right? So the back end of this arrow to the front, to the back end of another arrow to the front. So my vector, my resultant vector, comes down like this. So this vector I drew here, that's the relative velocity of the car to our truck. Okay, so there's that. The next thing we need to look at is at what angle is the car actually coming towards the truck. Okay, so this is the angle we're going to be using. The reason being is angle from where the let's call it the arrows start. So where the arrows starts, that's the angle we're looking at. And you can also try and imagine this, because if we're looking at the truck's perspective, as the truck is moving further up and the car is going further across, according to the truck's perspective, it would appear that the car is moving diagonally this way towards it. So diagonally this way towards it. So the angle in which we can work out how is it, or the degree in which it's coming diagonally towards the truck, it would be this angle theta here. So that's how you work out the drawings of the diagram. Okay? If perhaps we could even try and solve it. So we have the car that's going at 80 kilometers this way, 70 kilometers this way, and then our resultant, which is V2T. Okay, I'm just going to let this be VR resultant, just to make things easier. So the relative velocity we have here is 80 squared plus 70 squared. Okay, and I'll do the answers in a second because I don't have the calculator right next to me. And because this is our relative angle here, so theta is equal to inverse tan, so that's our adjacent side, and that's the opposite side, so it's 70 over 80. Okay, so I'll just quickly grab my calculator, see what answer do we get. Okay, so we have 106 kilometers per hour. Okay, should have said that's per hour. And then the angle we have is 41. Okay, obviously these are just roundups, but doesn't really matter. So I guess the final bit is just working out the actual direction. If we actually look, this is going west and then coming down south. So what we have is west 41 degrees south. Okay, if you want to make south the big one, or the one that determines the direction, you could write it as south 48 degrees west. And the last one we have is bearings. So you could have, let's see, and the bearings should be approximately 228 degrees. Okay, so that's how you do that one. Let's look at a scenario where they're moving away from each other. So again, we're trying to find the, according to our equation, we're trying to find the relative velocity of this car up here, according to the truck. Okay, so if we have a look, VC is positive, VT is negative. So VT is negative. This is going up this way. That's negative VT. And if I want to draw out the resultant vector for the scenario, it goes all the way across like that. Again, remember where this arrow begins, that's the angle we want to look at when it comes to relative velocities there. Okay, so that's how you draw this one out. Again, if we try and do the calculations, this is 80 kilometers per hour, that is 70 kilometers per hour. We've already worked out that the resultant vector will give us a relative velocity of about 106 kilometers. So that hasn't really changed, but the angle has changed. And so if we look at it, tan inverse is we have the adjacent side and we have the opposite side. So that. From before we found that that number was about 41 degrees. But as you can see, that 41 degrees doesn't imply the same direction though. Okay, because the truck is going north and the car is going east. So in this case, we have a bearing. This is the bearing of 41 degrees. But the actual directional angle, if we want to look at it, is north, 41 degrees east, moving at 106 kilometers per hour. So that's how you do those kind of questions when it comes to relative velocity. Okay, so the other scenarios that they do look at is if you are on a boat or crossing a river, motions between two cars, we've already looked at that, and then a plane going through crosswind and those kind of scenarios there. Now there are some other questions in the lesson for you to do. Let's just do one more before you can try it out on your own. So you have two cars, okay? You have the blue car that's moving at 50 kilometers per hour east. So I just draw that out, 50 kilometers per hour east. We have a silver car that's moving at 60 kilometers per hour north. We want to find the velocity of the blue car. So in this case, that's going to stay positive relative to our silver car. That's going to be negative. Okay, so if I draw out firstly, let's write out the vector equation, and that would be V blue to silver is equal to positive velocity of blue car and the negative velocity of our silver car. So if I draw that out, okay, our silver car or our blue car is going in this particular direction. Our silver car is then going down in this particular direction here. Okay, you can do it in a way where the vectors match up with each other. Okay, so the resultant velocity comes down this way, that is VB to S. This is VB plus, this is VS minus. Okay, so according to that, where the resultant arrow starts, which is this point here, that is theta that we're looking at. So let's firstly look at what V is, or the relative velocity. So that's 50 squared plus 60 squared, and root everything. And that gives you an answer of roughly 78.1 kilometers per hour if we do it to 3 significant figures. The last one we have is the angle, so tan inverse. We have 60 on top because that's the opposite side, and 50 on the bottom because that's our adjacent part. So inverse tan 60 over 50. That gives us an angle of 50.2 degrees. If we look at the total, or if we're looking at the actual direction, it has gone east, so we can write east 50.2 degrees south. Okay, so that's how you do the questions. That's basically explaining relative velocity in 2 dimensions. We've gone through the example of relative velocity for 2 cars. We haven't gone through the ones with the river and the plane, so that's what we'll look into later on as well. Now, that is it for this little explanation. If you want to look on to the other examples, hopefully there'll be a playlist uploaded as well, and you can watch more of it.